We have been discussing last time on the most important membrane contactor operation that we have today. That was the membrane distillation. I told you the membrane distillation is not dominant technology as reverse osmosis, as nanofiltration, etc. However, is a fast-growing operation with a lot of interest all around the world, including Korea, and small industrial plant already in operation, not very big, not millions cubic meter of water, but 100,000. And the expectation is that it will grow very fast for different reasons that we have been discussed. Possibility to operate with waste heat, solar energy, for example, on the very high rejection, possibility to have very high recovery factor, all limits of reverse osmosis. So some problem that exists in reverse osmosis, which is still quite interesting and important, can be overcome with membrane distillation. Today, we will discuss another interesting unit operation, which is not yet at the level of membrane distillation. So it's far away from reverse osmosis, but also is relatively new and not industrialized basically at all. However, if you go today on the literature and you click on the web, you will find more and more paper manuscript discussing on system where membrane operation and the crystallization are working together. Most of this work you'll find our names, because in our group we are working a lot on membrane crystallizers, but it's not only in our group. The system is growing and more there is interest in this. In this country, in Korea, if you go, and I was showing you in our introduction, if you read about how you will work in desalination for the next few years with Sierra 2, you will find that membrane crystallizers is one, membrane distillation and membrane crystallizers are typical example of the new area where research has to be carried on. So not yet big industrial application, but research. And basically, the motivation is that there are new approach for solving some major problem which still exist today, as brine disposal, and that's a typical case in which you can operate, or availability of raw materials that are disappearing, as with in some other case with water stress is also present, etc. Now, in general, crystallization is a very important unit operation in process engineering, and is one of the ways in which you can formulate most part of your products. When you just produce something, can be a drug, can be food, can be materials of any kind for any kind of application, at the end of your production, through chemical conversion eventually, purification, through separation, using membranes, eventually other system, at the end, you have to formulate your products. The way in which you buy in the shops or in your, and normally the formulation is emulsion, crystals, powders of different form, but crystals is one of the most interesting and important, and also is characterizing most of the expensive products. A lot of drugs, some foods are always appearing as crystals. And so you can see here that the final formulation of a lot of products sometimes is some biochemical or farm drugs are 90% are in the form of crystals. And the same is a lot in personal care products, not just toothpaste and different kind of soap. More and more, these systems are becoming important in much more sophisticated application as organic semiconductor, single crystal based on device and photonic crystals, catalyst. This is one of the areas where crystals are quite important, and advanced drugs and chemicals that people are using for a lot of the different applications, from control release, etc. That means a lot of interest is for this kind of unit operation and how also to improve eventually the way of doing. How people are what they are doing today to crystallize for the different kind of application. There are different ways to crystallize everything. One way, the most traditional and the most used one, is just by solvent evaporation. Just to crystallize, you have a solution. In this solution, there is a solvent, let's say water in our case, and you have some chemicals at a concentration which is lower than saturation. In this case, there is just an homogeneous solution eventually. If you just eliminate and you reduce the presence of the solvent, you concentrate your solution. At one point, you are approaching saturation. And when you're approaching saturation, from homogeneous system, you arrive to have a heterogeneous system where the solid phase that can precipitate when you approach at a certain temperature, this is a thermodynamic equilibrium, dynamic thermodynamic equilibrium. At a certain temperature, you will have equilibrium between the solid phase and the solution, in which there is a continuous exchange of molecules that are going from the liquid phase to the solid phase and vice versa. And that's a typical dynamic equilibrium of all the chemical equilibrium. In this case, you are in presence of what we call a saturated solution. There are other ways to realize this kind of situation, which is not just by solvent evaporation. Keep in mind that what is more important in crystallization is to create what is called supersaturation, a system in which concentration is overcoming the level in which you can have just the saturation and precipitation. And the local supersaturation gradient generation is one of the key parameters for having a well-controlled crystallization at the end. Because what you have to do in this case, you have to try, when you're just working in solvent evaporation, to control the evaporation rate, control the energy necessary to produce this evaporation. See, these are the parameters. This is the local supersaturation gradient generation is one most very important factor to have at the end high quality in your crystal. We will see what does it mean, high quality. Other way of doing is batch cooling crystallization. Instead of warming up, you can also cool down. That's another way of doing, and you have the same result. Normally, when you are working in batch cooling crystallization, you're not easy to reproduce the performance of the system. You have very easily inhomogeneous supersaturation distribution. Just what we have mentioned before is very important. Here it's very difficult to keep control. So if you want to have high quality crystal with what we call low variance, very small size distribution of the size of the crystal, etc., batch cooling is not the best way of doing. There are some other way of crystallize. In interesting way is this anti-solvent or drawing out crystallization. That means you can just remove in different way the solvent, or you can introduce some other species which are not solvent for the chemicals which were dissolved in the solvent number one, in water. So if you just start to penetrate with a solvent which is not water for a species solvent, you can have an anti-solvent or drawing out crystallization. Keep in mind that in this case, this thermal evaporation and today also anti-solvent are the way where membranes are going to play a role, a quite interesting role. If you want, I was mentioning before, more and more, there is attention to how to crystallize. A lot of conference on just crystallization. There is a university where they are working today in Europe, in the Netherlands and the UK, on formulation engineering. That means how to produce at the end your products. And crystallization, emulsification, condensation, etc., are a key class where students are learning how to formulate your product using this kind of technology. For doing this, because it's important to try to improve as much as possible in terms of quality, cost, etc., the way of doing, and the request for high control in crystallization is normally how to control crystal size and size distribution, what we call variance of the dimension of your crystal shape and habit. A very important parameter, what is called the production of polymorph. Most part of the crystals don't exist in one single habit. They can, the same chemical composition can appear in different form, and this form can have very, very different properties, to the point that in some case, some of this form can be useful as a drug. In some other case, they can kill if you just have the wrong form. But in any case, they have very different performance at the end, just for the habit. And one typical example, extreme case of the polymorph is an enantiomeric purity. You see, you know that there are many compounds, particularly drugs and also in food, which have the same chemical formula, but very different behavior. And these are what we call enantiomeric species, which are my hands, which are compounds, let's say there's a compound very similar, exactly the same, also space configuration, except for one point. They cannot be overlap. They are just similar, but face to face. One is right, one is left. And this is in our body, in nature, for some strange reason, most part of the interaction of these biocompounds, racemic, are with the levo form, not with the right form. The right form, at the best, is going through with no interaction with the receptor where they are supposed to interact. The levo form, for most part of the amino acid, are the ones that really interact with the body, in nature. In some cases, unfortunately, if you are just using the wrong enantiomeric compounds, the drugs which is right instead of levo in its racemic composition, you can have big trouble. Thalidomide is a typical example that everybody knows. We have been creating a big disease in some countries where some drugs have been used. No one was aware 10, 15, 20 years ago about this problem. No one ever tested before to supply a drug with a very low enantiomeric purity. So there was one compound, the levo form, that was active and giving some positive results. But if the purification of this compound was not good enough and some right form was present, big trouble in the ears. Not immediate disease, but children were born and they had a lot of terrible disease or malformation, etc., etc. So now we are aware of this. So the enantiomeric purity is one of, which are of the crystals, is one of key issue. When you buy any drug, you have to read on the label, on the back, which today by law, which level of enantiomeric purity is present. And if it's 99.9, you are pleased. If 50%, you must be worried. And what is the other 50? And normally the other 50, we have no evidence of any negative effect in 10, 15 years of experiments. We never know what will happen in 300 years. And that is one of the problems still existing. Today there is a lot of attention, by the way, to shift towards crystallization of organic and biomaterials, which was not very traditional in the past. And in some cases, because you are using this organic material for some reason. In some other cases, because you need the crystallization to understand life. For example, we crystallize today protein, not because we need protein in crystal form, but because if you crystallize your protein, you can understand, for example, a lot of phenomena, how this drug can interact with the specific size in the protein configuration, etc. And so that having good crystallization of a protein is one of the most important issues today for understanding how life works. And in the last 10, 15 years, 3 Nobel Prizes have been given to people who have been able to crystallize protein, which are also enzymes. Enzymes are protein with catalytic activity, and that they control most part of the phenomena in nature. That's why if you want to understand how these catalysts work, you can try to produce crystals, and from the crystal You can identify interaction, transformation, etc., etc. So this is another part of the story, not for large industrial production, but because we need for. Where is the interest for membranes in crystallization? The driving force for the crystallization process is to create supersaturation, to create this step in which you start to create what is called a nucleus, and from the nucleus after you grow your crystals. And that is happening in this step of the supersaturation of your solution. If you don't control supersaturation in the right way, you can have some negative aspects or some positive aspects. For example, when you have too high supersaturation, you have an excess of nucleation. That means you have a shower of very small crystals. If you have a low supersaturation, you have very few crystals and you have very slow crystallization kinetics. The growth of the crystal is basically quite low. You can have also very often a supersaturation which is non-homogeneous. We saw, for example, when you have, by cooling down, that's easy to have non-homogeneous. And in this case, just the opposite than the low, you have very broad crystal size distribution and not equal. Particularly in some application, as a drug or in catalysis, you want to have all the crystals as much as possible similar one to the other, and you decide which one is right. So if you want to improve the performance of your crystallization, basically you have to find a way to have a very good control of the supersaturation step. That is the point on which you have to operate. And if you are able to do this, you can have a control on the morphology, that means on the crystal size and size distribution of the same crystal, on the shape, on the habits of the final crystal, and also on the structure. You can have better control of the polymorph, pseudo-polymorph, etc. Membranes can do the job. Initially, the idea to use membranes was just related to the fact to introduce a different way to evaporate the solvent. Working on membrane distillation, we have been learning that basically in membrane distillation, if you remember, the transmembrane flux across your membranes is basically independent from the feed concentration, very different than the reverse osmosis. In reverse osmosis, if you just change the concentration of the feed at the membrane interface, you are killing the process because the driving force, the delta P minus delta pi is increasing. If you have a constant delta P, the pressure you apply, and delta pi is increasing because you are increasing the concentration, the effective driving force is decreasing, and transmembrane flux, which is proportional to this delta P minus delta pi, is decreasing. So you just go down, as you remember, with our transmembrane flux in reverse osmosis. If you do the same work with membrane distillation, we learn that basically increasing the concentration at the membrane solution interface does not affect significantly the driving force in the transmembrane flux, which is just because it's in the evaporation, it's totally different mechanism, and just you have a small delta T that is moving the molecules in vapor phase across the porous membranes, and so there is not the same effect. Eventually, you can have an effect in terms of viscosity, that the viscosity that is increasing if you increase very much, or you can reduce the activity, and that is reducing vapor pressure difference, but the effect is not the same as in reverse osmosis. So basically, we concluded in membrane distillation that the transmembrane flux is a constant, roughly constant, with increasing feed concentration. That means that we can increase and increase the transmembrane, we can continue to have transmembrane flux at any level of concentration, eventually, to the point to create a supersaturated solution in this, using this kind of methodology. And that was the basic idea, just starting and using, for example, just on this initially for protein solution, because protein is quite interested trying to produce protein in a very well-controlled environment, and to remove the water and to crystallize protein on the membrane surface, trying to reproduce what exists in nature. A lot of protein are present, bounded in membranes. We are learning, and now we know today, that the role of the membranes is much, much more than just helping the evaporation. Because the membrane itself, with the surface energy of the material you are forming, with the pore size distribution, and with the creation of interfacial phenomena, etc., is contributing much more than expected to the final performance of your membrane crystallizers, and as you will see. And basically, the idea was that you can have an aqueous solution. At the interface, you can have evaporation of the solvent. No protein will go in a vapor phase. And if you have a small delta T, few degrees centigrade, then it will be vapor going across, just water, and you will just recondense on the other side. So easy, simple, and just an extrapolation of the concept of membrane distillation at the extreme case. Solvent evaporation at the interface on one side of the membrane, and just the migration of the solvent in vapor phase through the pore of the microporous hydrophobic membrane that we have been utilizing, and condensation on the other side of the membrane following one of the different configurations that we discussed last time: direct contact membrane distillation, vacuum membrane distillation, air gas membrane distillation, stripping gas. For the moment, at least, we have these 4 different options, but as you can see, the mechanism was exactly the same of membrane distillation, except that you don't stop at a certain level of water production. You want to concentrate as much as possible in here. In doing this, you must be careful, because we know that if we concentrate too much, we can have fouling phenomena, and that will be one of the major points to keep under control. Basically, driving force in membrane crystallizer, exactly what we discussed in membrane distillation, can be, we have just different in vapor pressure across our membranes. It can be a temperature difference. Consider that we can also have a concentration difference. As we had membrane distillation and osmotic distillation, something similar to pressure retarded osmosis, we can also have here a concentration difference, and we have osmotic membrane crystallization if we're working on a crystallizer. And that's, or you can have a thermal membrane crystallization if you have just a delta T across your membrane. And that is basically to create the supersaturated solution. And in the supersaturated solution, you can induce nucleation and crystal growth. Crystal growth will not take place in the same part of the system where you have nucleation. That is one of the problem and difficulties in the system, that if you don't want to increase too much fouling problem and losing the transmembrane flux, you have to try to nucleate and to grow the crystals in different parts. That means you cannot try to grow the crystals on the membrane surface itself, except some situation in which the value of the crystal is so high that you have no problem in changing the module or cleaning the module every 2 or 3 or 5 hours. But if you want to produce, for example, fresh water from the sea at a very high recovery ratio, that means that there's a lot of salt, you have to separate the nucleation from the crystal growth. And that is a typical example. So what you have to do, if you have your membrane module, you will try to create a supersaturated solution in the module itself. So you induce nucleation, which is the first step, as when a child was born. The first second is just very important. The same is here, but the real growing of the crystals will take place in another part of the system, another body, where you can also form the crystals and continuously remove them. So in such a way that they will not go back on the membrane surface, so they will not plug the system, they will not. That can be done in different way, controlling the fluid dynamics, or you can control, for example, the temperature. You can have a certain temperature on the membrane surface and another temperature in here. And so you can have the kinetic of the crystal growth will be very, very slow in here, but very, very positive on the other part, depending how the change in temperature can affect the kinetic of the crystallization. And that's something that people are learning. Another very important aspect that we already predicted when we started was this one, that this is, no, first of all, most part of the normal crystallizers normally are batch system, discontinuous crystallization, not continuous one. With membrane system, as basically most part, if not all membrane system, you can have a continuous crystallization. That means you can, as we told before, continuously produce crystals and remove them from the system. But what is more important, that in normal crystallizers, to have a high homogeneous crystal formation, etc., is not so easy, because you have big pot and you have to, the evaporation is not easy to control where it happens. You can have an area where there is stagnation, you have to have big mixing, etc. In membranes, in principle, if true what we are talking, for each pore is a place where crystallization takes place, where a certain level of concentration can be reached. So you can have a quite homogeneous distribution of the crystal that you are going to form. So it's much, much easier and much more control to have a kind of homogeneous system. So the heterogeneous final result that you have in normal crystallizer, in this case, by definition, if these pores are as much as possible all the same, in the same configuration, you can control concentration on one side, concentration on the other side, size of the pore, etc. So you have all the parameters controlling the supersaturation and the crystal formation would be basically point. As you know, along the this was assuming that you have a membrane fiber, you can create a very uniform supersaturation profile in the process. That will, in principle, that was one of the predictions we were doing. You can have yielding uniform distribution of early crystalline nuclei. And that, in fact, is one of the points that has been very easily demonstrated from the very early stage. If you just study the crystal size distribution using this kind of approach, and you just plot the frequency of a certain dimension, in certain habits in your system as function of the crystal size, you will see that changing the different also the linear velocity, but you see here, if you don't have the membranes, that is the typical distribution in a traditional batch with no membranes. When you introduce your membranes, you have this kind of frequency of appearance of a certain geometry in your system compared to the other one. So you just and that was related to the assumption that was done and has been very early verified. Enzyme crystal can be obtained in much more uniform size than normally obtained in a batch system, and you can have the possibility to produce a large amount of uniform crystal size, and that was the conclusion already about 8-9 years ago now in protein crystallization. That was quite interesting. I was starting this story because, as I was mentioning, to crystallize protein is not easy. And in some cases, it was impossible, by the way. The point that if you do a new way and you crystallize some new protein, you have Nobel Prize. So if you want to try, that you can still know. In the last years, there was 3 Nobel Prizes given to people who have been introducing new way to crystallize protein. The membranes are doing something interesting. That's one of the expectations that you had. The porous structure, that means the porosity on the membrane surface, which means some kind of cavity and a certain level of roughness, maybe this porosity can entrap protein molecules, leading to localized supersaturation maxima, very high level of concentration, very localized just on the mouths of in the pore on the membrane surface, that promote the nucleation and the formation of crystals at condition of supersaturation that will have been inadequate or insufficient for homogeneous crystallization. You can read here the reference. Journal of Crystal Growth and Design is not a membrane paper, is not a membrane magazine. This is the official organ of the American Chemical Society for experts in crystallization. So they have been learning, and they are using this concept as the front page of their magazine to show new way to obtain some results. So it's not just the membrane people telling how good it is. This is the expert in crystallization that for the first time they realized this can be the way to solve our problem in crystallization, particularly in large molecules as a protein, and to realize something that they have not been able to do in traditional batch crystallization, basically. And that's, in fact, has been quite interesting. But very quickly, you can learn something more than this, because what you realize, the first time that the students came to me with some of the results of this crystallization, they came to me and they said, there is something strange. You told us to be patient and to wait for 1 week and 10 days to have the crystals. And we have the crystal in 1 day or half a day. And I say, look, you are just naive, you are just a student. Go back and repeat the experiments. Because probably what you are crystallizing now is not the protein, it's just the buffer. Because you know, when you have a protein enzyme, they are stable in a certain range of pH, so you only have to work in a buffer. And buffer is sodium acetate and or carbonate, etc. together. So my first reaction was the crystal that you had in such a short time are just crystal that you are forming by supersaturation of the buffer of the salts, not of the protein. Check again the experiment. They check again, they went to the X-rays, they made the experiment, it was protein. So I was wrong, they were right. And so we said, what is happening? We were in literature, we expect to have crystallization in 3 days, in 1 week, 6 months in some case, and we have in few hours or few days. So we started to try to understand, and it came out that the results were correct. So the membranes was not only acting to evaporate, was also inducing, changing the activation energy of the controlling the kinetic of crystal growth. You can, if you check already in the literature, the effect, the difference between the Gibbs free energy difference of the heterogeneous system compared to the one of the homogeneous system. Homogeneous was traditional crystallization when you are working in a solution. Heterogeneous when you are on the membrane surface. Already people were expecting quite interesting effect in reduction of the heterogeneous activation energy. That means heterogeneous, the difference between the Gibbs free energy compared to the homogeneous one. In fact, now if you make a systematic study going from Teflon to PP, etc., you see that this reduction is becoming bigger and bigger in a certain direction of your polymers, in the surface energy, for example. All the strongly hydrophobic, the one we have been using because we want to use membrane distillation basically, and there was hydrophobic material, Teflon, PVDF, etc., much higher than traditional acrylonitrile, celloacetate, etc. So this result was exactly what we were supposed to have, understanding in advance what was going on. So this second effect, very important, is that the activation energy of your system can be significantly reduced as a function of the hydrophobic character, that means contact angle of your membrane. So if the contact angle is increasing, arriving to super hydrophobic membranes or a very high membrane, you can still have a higher reduction of the activation energy. That means speeding up the formation of your crystal significantly. That's quite interesting effect that today is under investigation. Everybody now is looking into this and find membrane that can not only as function of the intrinsic hydrophobic, but also in terms of the apparent hydrophobic character by checking the roughness of the surface, the distribution of the pore. All these effects are quite interesting because they can create the situation for this kind of effect. Traditional equation that we have been discussing already in membrane distillation is also to be considered, and if you want to understand this variation of the delta G heterogeneous to delta G homogeneous, we already discussed a little bit, and here it's becoming more and more significant because you have to introduce, and this now is an effect directly on the activation energy, is an effect that related to the contact angle for sure, but also to the porosity, and more than this, just know this, when you have your pore, here remember that you have also, this is not flat capillary, you have some other force which are active here. And that is this kind of the curve, the level of this curve, which is also a function of the hydrophobicity or hydrophilicity and of the size, can have an effect in some deviation of this kind of equation, which is the Young equation modified. But now we understand that this equation is related to the delta G of our system, and is related to the kinetic of the crystal growth, which normally people were not considering in traditional study on this kind of effect. To the point that, again, this delta G, you can, heterogeneous compared to the one homogeneous, if you study carefully as a function of the contact angle, you will see that not only is a function of the surface energy of the different polymer you're using, but also of the level of surface porosity. So this epsilon that we introduced already, which is the effective porosity of your material, but basically the surface porosity. Part of the surface there are pores, part is not. So this is quite interesting and is present here. And if you go from surface porosity 0, and you have this kind of phenomena, otherwise you have the other one, 0.4, 0.2, 0.3, etc. So both, all the parameters which characterize a membrane are quite important, not only for helping the evaporation, but for promoting this delta G heterogeneous, delta G homogeneous, and that means kinetic phenomena related to. Kinetic phenomena is not just speed in crystal formation, can be much more than this, because we will see very soon that when you want to study, and we were mentioned before, one of the dreams is how to control a polymorph at the end, how to produce an enantiomeric form with very high level of purity. Now, if you have one way to solve this problem is to have a control in the metastable phase of the supersaturated solution to control the kinetic of the crystals of some intermediate products. That's the way to change completely the final product you can obtain, and we will see the situation. So what is important at the moment is to understand that we are not only evaporate and doing what can be done just warming up your solution, but we are introducing new parameters that can just having an effect on the delta G heterogeneous on delta G homogeneous, can have an effect on the kinetic of crystal growth, for example, and on the other parameter important. And experimentally, the nucleation rate, that is the most important parameter we have to keep control. In terms of the porosity, you can have, you don't have very simple, these are just a protein that you can try to crystallize, but basically the trend is quite interesting and just the one that we were anticipating before. And that is again that data that now in the physical chemistry are well understood and well published in the literature, you can find them. There is another interesting aspect in which membranes have a role. One way to predict, to try to understand how the different molecules, nuclease, interact each other, and after they produce crystal, is to introduce some probabilistic parameters. This Zeldovich factor zeta is a probabilistic parameter, a statistical analysis that is telling you when you have already some molecule that aggregate, they meet together, and another one is arriving. The other one that is arriving can still interact or can be rejected. And depending from how this system works, you can make some statistics, some just probabilistic analysis, and at the end you have this pre-exponential term of the traditional nucleation expression for nucleation rate equation. So this is the term that this Zeldovich was introducing. What's interesting, and obviously this term now can be modified and utilizing the delta G that we calculate for this porous material, introducing this porosity factor epsilon, etc., etc. And so you can have at the end a Zeldovich factor for the heterogeneous porous material and the homogeneous system. And that is the equation that you have. Now, if you do this kind of analysis, and you just go now to see theoretically from this analysis what is coming out, this is the behavior that you expect in terms of Zeldovich factor, which is exactly the kind of, at least qualitatively, the kind of performance that you saw before in the experimental results that we are doing in the formation of real crystal of different proteins, etc. So all these analysis of the Zeldovich can be easily transferred to this delta G heterogeneous, delta G homogeneous for microporous hydrophobic membrane with a quite interesting agreement introducing the different parameters characterizing membranes, porosity, surface porosity, etc., etc. This also was a quite interesting effect. This is important because they start to give you some thinking what can happen now if I want to be more sophisticated in my crystallization. For example, if you try to have the heterogeneous nucleation of paracetamol. Paracetamol is very well known. Most of you, most of us are using sometimes in different formulation. Paracetamol is an anti-inflammatory product, very common. And you can just try to, and as most part of this drug, paracetamol exists in different final polymorph. You can have paracetamol 1, paracetamol 2, or maybe also 3, but at least 1 or 2. And you can try to understand what is happening when you crystallize paracetamol not using traditional homogeneous batch system, when you go in this kind of heterogeneous crystallization. And when we start to make this crystallization of paracetamol, what came out that we found that we were able to separate paracetamol polymorph 1 from paracetamol polymorph 2, just by changing the traditional parameter that you can control in traditional membrane operation, changing the transmembrane flux or changing the cross flow on the membrane surface, basically. So what is happening here? That's quite interesting, and you see that is the separation that you can observe, and basically you can at this stage already summarize that from this first result, the function that the membranes introduce in crystallization is much more, that was mentioned, than what we were expecting at the starting. You have a mechanical effect and chemical effect. So what you can do, you can speeding up the crystallization kinetics and obtain crystals in a very short time instead of months or days, etc. You can have in hours or much shorter than normal. You can obtain crystal in conditions that are not normally possible, not adequate for normal crystallization, taking profit of the specific function of the morphology and the surface characteristic to create local high concentration of your solutes, such a way that you can induce crystallization. And much less amount of initial substance can be needed, for example, if you just concentrate in the surface of your membranes. Macromolecule can, almost part of this work was done to high molecular weight species. Also, when they are very reluctant to crystallize, you can have situation which can induce crystallization. We are trying to crystallize any difficult protein. In some cases, we don't succeed. In a few cases, we've been already succeeding. More important than everything here, you can do all this kind of interesting improvement in a continuous crystallization. And that is one of the points more important. You can crystallize, making the crystallization a continuous process, not batch system as most part of the crystallization were before. Just to give you an example of some of these proteins, these are the lysozyme, and these are some of the best crystals never produced on Earth until now. If you go in these are all if you make this synchrotron lyse analysis, the quality of this crystal is the highest one in some case, or similar to the same crystal obtained in the space lab when you are working with no gravity, etc. You can have this kind of formation, the same level of quality than we have in a membrane crystallizer. What's also very interesting, if some of you will work in the future, look this one. This is a trypsin. Trypsin is another protein. If you have an idea of biological, our membranes, you remember that we have normally a double layer of lipids, etc. And normally there are proteins that are just going across. And these proteins are the one that is the highway for moving water molecules, these aquaporine or similar, or to transfer signals. This is a trypsin and growing on the membrane surface, entering in the substrate, that is our membranes. This can be the phospholipid bilayers, and going across. We are not producing too much of this crystal also on the other side, but if you have able enough, and that is going to happen, you will have this one going across the system, and if you apply here your signal, this signal will be transferred on the other side. So this is one, from my point of view, the most interesting visualization of an artificial biological membranes, because this is instead of having the double layer of your phospholipid, you can have a layer, a porous layer of your PVDF or polypropylene or HALAR or what it is, strong fluoropolymers material in such a way that you have all this behavior, and the protein growing from one side to the other. Quite interesting as future development. Now, let's go back to the polymorphism, because when we started to observe with paracetamol, the fact that we were forming, in some experiment, paracetamol 1, in some other experiment, paracetamol 2, that was just creating a lot of curiosity in our students, in ourselves, and so we started to try to understand. We were not very expert of this kind of thing. We were expert in membranes, but not in all this story. So what is the polymorphism? And that you learn quite from the literature very, very quickly, what is happening in the system, where you can have the different steps. You can have the you have nucleation, and what they call a conformant 1, conformant 2, and the very, very early stage is already giving some information to what will happen later on. And you can have now the pre-nucleation and the first crystal nuclei and the growth, and you have this kind of final habits. In the other case, if in any way you can produce not conformer 1 but conformer 2, you can have a different prenucleation aggregate, and you can see physically these molecules are all the same. There's no change, no chemistry involved in this case. Everything just probabilistic factor, how they aggregate, how they meet together, how they put the order, as function of the environment in which they are moving. That depends from the velocity, from the influence, from the radiation, from everything except chemistry. Chemistry, nothing changes here. Everything is the same, basically. But you can have this in the metastable phase of the nucleation, different kind of pre-nucleation aggregates, and those are the ones that later on are giving to totally different kind of final polymorph. And these two polymorphs have total different catalytic effect or interaction with your body, etc., etc. So quite important. And the difference between the polymorphs normally are not in the chemical properties, but in the solubility, rate of dissolution, melting point, stability, hardness, eventually plastic deformation, optical properties. They are no more acid or more basic. They are just property of this kind. Now, what was happening to us was that, for example, again, I think this always, unless it was glycine. Glycine is an amino acid. So the same phenomenon we were observing with paracetamol, we start to work with a little bit systematic way with some other compounds, typically forming different polymorphs. Glycine is a typical that all of us have been interacting with glycine, as amino acid we have in our food, and you can have a glycine in the polymorph gamma or in the polymorph alpha. And at a certain pH, normally you have only alpha form, and you can have, in other situations, you can have a different kind of polymorph, the gamma. It came out that in our study, we are able to separate alpha from gamma just changing the flux across the transmembrane flux across the membranes. We learned that in the form gamma was low transmembrane flux, the alpha, if I will remember, was in high transmembrane flux. If the flux was 7 or 13, or if the fiber was 34, you have different for gamma or on alpha. And so that was one of the quite interesting example of the result. And physically, that can be just a big difference, you see. That is the gamma, and that's the alpha. And you can start to see here that these two forms are very different in terms of also the final geometry and you can have an idea that in some low flow rate was giving this form, and high flow rate is this other one. So there is an effect of the velocity on the membrane surface that can orient, that can facilitate in this probabilistic interaction one form to the other. And that was exactly what we have been observing initially. Increasing the high flow velocity on our membrane surface, we were producing crystals with more elongated, as you can expect. And when you are very slow cross-flow velocity, the crystal were forming in a configuration, which is exactly what you expect. But we had no idea that that can give you the possibility to separate, in this form, gamma from alpha, and realizing one of the dreams that is still necessary today. Quite interesting. So the control of the rate for the achievement of supersaturation allows to switching from a kinetically to a thermodynamically controlled nucleation stage, triggering the production of either a stable or metastable form. What is happening here? What is happening here, by the way, these are, again, same story that I was mentioning before of paracetamol. You can see here the same kind of phenomena. You can have the form 1, the form 2, depending from the different parameters characterizing your normal membrane operation, which we are used to effect. And the final results, like you can see here, how different they are. Quite significant different. What is happening? Still, each of you can give still work in giving more contribution to the understanding what is happening here, but in principle, that can offer you the way of thinking and which can be the solution of the problem. Because what we are talking about is that we are increasing significantly using some polymers with some level of porosity and some kind of surface properties in terms of cavity of your pore, etc. We are just, when you just move from one species to the final one, as you know, you have to overcome barriers that are called the activation energy of your system. And if everything is regular, at the end you have a crystal that is thermodynamic stable, the one that is normally formed in terms of potential energy of the reactant compared to the product of your reaction, if it's a reaction. And that's exactly what happened. But in the meantime, we have a metastable phase in the crystal formation. The metastable phase, normally, you are not taking too much care because the metastable phase, they are metastable. So slowly they appear, but they disappear. And depending from the velocity in which they form and they disappear, eventually, in some case, you can have some effect, but normally negligible. If you are using membranes in your crystallization, what is happening? That you are changing not only the kinetic of the thermodynamic phase, which is at the end will be the same, but you can have a significant control on the metastable in the form that you are creating in the metastable phase. Now, if you speed up, if you reduce the kinetics, the activation energy of some of the metastable phase, you would crystallize them very quickly. So they will never arrive to the thermodynamic stable phase at the end. So you are introducing a strong variation in the mechanism of formation of the final product because you are able to control all what happened in the very early step of your metastable heterogeneous nucleation phase. Okay? So if you're doing this, and you can start to calculate and to see if your prediction can be valid or not on the thermodynamic, but on the kinetic crystals. And so the one that we are forming and controlling in our condition are the fact that we are having an acceleration of the kinetic crystals that we remove from the system, so we have a final formation of compound that in the traditional system we're not able to arrive to the thermodynamic stable phase. That's quite interesting because this is true, and we are working to, we means you, these good students are working to try to confirm this kind of thing in a very different kind of situation. That is quite interesting, the most interesting aspect of membrane crystallization, because in this case the possibility to control metastable heterogeneous phase is related to the property of your membrane, to the porosity, to the roughness of membrane surface, to the size of the pore, etc., at a different level of sophistication, because it depends from the depths of the pore, for example, in some cases, etc., etc. Quite interesting in perspective. To the point that now, going back to the real life, this is still something that has to happen. But today, as we discussed about in the Korean Sea Hero, the idea to use this kind of logic to produce not just protein crystals or polymorph of paracetamol, etc., but to solve the problem in desalination of the recovery factor, of the fact that we have a lot of brine, that we know what to do with this brine, and we just have to solve. We produce water, but we create a lot of problem with the brine disposal, etc. So you remember that in a European project that was done in Europe and finished a couple of years ago, where all these big universities in Europe and also big company, Veolia, for example, was one of our partners. So not only professor, but also big people involved in water. The idea was at one point to have a nanofiltration reverse osmosis process to introduce, to make more interesting system as pre-treatment to a reverse osmosis nanofiltration, a lot of membrane operation, as microfiltration, ultrafiltration, eventually also some membrane bioreactors at the end. But what was the most important, on the concentrate of reverse osmosis, or also eventually nanofiltration, when RO does not work anymore, because transfer at certain level of concentration, driving force is going to zero, basically, there was no flux across the membrane, we were introducing membrane distillation and membrane crystallizer. Initially, only membrane distillation to increase recovery factor. Instead of stopping at 50% recovery factor, in this case, you can arrive to 90%, 93% recovery factor. But slowly, we have been learning that not only you can increase recovery factor for produce more water, you can increase recovery factor to the point that this recovery factor is approaching a value for which you crystallize, as we saw before, your solutes here. You crystallize your solutes, so instead of producing just water, you produce water on one side and the crystals on the other one. And that is opening a totally new venture that Korea is a protagonist, because you will have in the future, in the next 4 or 5 years in this country, a lot of attention to use this concept to not only to produce water, but to produce raw materials in a formal, appropriate to a lot of utilization of high value, particularly electronic industry, catalysis, pharma, drug, etc., etc. And so that is just related to the fact that the crystallization that we saw before works, and not only works, but works better than expected by initiating. Not only the evaporation and to increase recovery factor, is to produce crystals of high quality in the right form, eventually in the polymorph. Polymorph is not just for protein. Polymorph is for everything, including most parts of the crystal which are present in the sea. When you create, for example, magnesium sulfate. Now, magnesium is a very important product today. Magnesium is a strategic metals. More and more in the future we are going to use magnesium. Magnesium is very light. Today people are working or in the United States, in Europe, probably also in this country, to produce some new alloys where magnesium has a role. That means you can make plane tomorrow, train, automobile, much lighter than the one we are producing today with iron, etc. So magnesium is becoming important, is already important for drug application, other things, but will be much more in the future. 90% of the magnesium today is produced in China, and they're producing this by solar pond, just from the sea. Now, if you just analyze what is happening in the sea, and in this step here, when you are using nanofiltration, here we can separate easily magnesium from sodium chloride, etc. Together with magnesium here, there is also calcium carbonate. We will see we can separate calcium carbonate. We precipitate calcium. We have basically magnesium with some strontium, some barium, and all the monovalent are going in permate in RO. So here, if you just induce a membrane crystallizer on the nanofiltration concentrate, you increase recovery factor, but you can produce magnesium sulfate. You can do more than this, because if you follow now the instruction and you learn what is going on, you can analyze in which condition you can produce not magnesium, but magnesium sulfate with 7 molecules of water is called epsomite. Epsomite is paid on the market $14, $15 per kilo. So as I was told you before, forget about the water, you just produce epsomite, because that can be the real problem. The water is for free. You give to the people for enjoying, but the market is the epsomite you can produce if you really produce this kind of form. And membrane crystallizers are doing the job. You can produce basically this specific form. You can produce epsomite if you control ionic strength. Remember the ionic strength, what it is. Ionic strength is the concentration of your solution, but taking care is the real term that keep controlling from a thermodynamic point of view of your difference in chemical potential, etc. It's not just this is the product of the concentration for the square root of the charge of the ions forming your system. And that's a strong effect on the final performance. And so you can, what has been suggested already a few years ago, as in the nanofiltration, first you precipitate all the calcium, so you don't, because calcium otherwise is the first one to be saturated and to be crystallized. So you have to separate the calcium, and when you separate the calcium, that can be separated 99% basically with putting some CO2, for example, so you can form calcium carbonate. And after you go in this step, and you control the appropriate ionic strength, pH, concentration, etc., and the membrane system will give you just epsomite, basically 100% epsomite. It's not so easy, it's much easier telling you the story than realizing, but that is actually what can happen. Keep in mind that in the same logic, if you apply now in seawater desalination, all the benefits we are mentioning are present here. You can see here that sodium chloride crystallization at the end of the story, these are the kind of crystal that you can extract from your brine disposal problem that was how to solve the problem was a tragedy. Now you create crystals which are quite interesting with a variance that means the standard deviation compared to the mass-based mean size. That means the deviation of this size of the crystal compared to the average number. Normally in most part of the system this is about 50% at the best when you have very good crystallizer. With membrane system, you have a variation of about 15, at most 30. So the quality of this crystal size distribution, compared to the crystal length, is much more sharp and regular than the one you have normally in traditional system. And that is, this 50 is becoming 15 when you are smart, or at most 30%. And that is one of these quite interesting results that for which now everybody is spending $70 million in your case here in Korea for having this kind of crystals. That is the epsomite you can crystallize. Again here you see very nice, relatively sharp pore-side distribution with interesting growth rate and very nice final habits of the crystal you are producing basically. And in the story was that today with the end of Medina, we can have an overall recovery factor introducing membrane distillation and membrane crystallizer. Recovery factor, for example, on the NF unit of about 95%, and you just produce not only, this is for single cubic meter of water, not only water that you go to the RO, but you produce also about 8 kilograms of epsomite and 35 kilo of sodium chloride and about 3 kilo of CO2. So what there was a problem, using this integrated approach is becoming quite interesting. And if you make a very preliminary rough cost analysis, you can also see here that assuming that some waste heat is available, so you don't have to spend too much energy in the distillation, membrane distillation and membrane crystallizers, basically you have a cost which is similar and comparable with the best cost that you have today in the most advanced RO operation you can have. This is about 60 cents of a dollar per cubic meter, which is the one that, but that is the assumption is that energy is available, waste energy is available, or solar energy has been utilized, and that is, so you save about the energy cost. Otherwise, this number also does not change too much. If I well remember, it will be basically double. These one are for different configuration of your integrated system. This is FS4, is the one I was mentioning with membrane crystallizer, membrane distillation on the retentate of NF and also retentate of RO. Quite interesting as preliminary study, and that's on this line where people are moving. I was mentioning before that, first of all, there are some problems. Until now, everything that we have been discussing are the interesting, attractive, positive effect that can have. Not so easy, as always. A lot of them exist that you have to try to solve. And some of the trouble, sorry, I just have some. First of all, you have to study very carefully what you have in your system. If you're working with a protein solution or with paracetamol, you have a water and your protein. And eventually this infused nanogram of concentration sometimes. When you crystallize protein, we are using one hollow fiber as a crystallizer. We have a few micrograms of solution sometimes, very expensive material. And so this is, membrane system can be for scaling up, but you're also scaled down. So you can produce a crystallizer, which is one of my hairs as hollow fibers, the one that Soo-Kyung will produce on the 10th floor, a single fibers, small piece, that is a crystallizer when you make the right assembly. Because you don't have too much material available, and so you just have a very small membrane surface, but it's useful. When you do in this situation, however, in seawater or similar, not so easy. You need huge plant. And you have to avoid, and you don't have water and paracetamol or water trypsin. You have hundreds of different compounds. So the first thing you have to learn a lot about salt precipitation and all this story about the solubility of the different salt when they don't precipitate, when they precipitate, when they will just overcome the supersaturated solution will be formed, etc., etc. The other thing that you have to learn is that when you precipitate something, I was mentioning epsomite, they are assuming only magnesium is coming down. Not at all. If you have any strontium present, that can be also very low concentration, 10 ppm or 50 ppm, etc., during the formation of the epsomite, you can have entrapment of the other bivalent ion, can be barium, can be strontium, and this will change significantly the crystallization story. Crystallization is a very, very complicated and delicate process. If there is any organics present in the solution, you don't form any crystals. You have to avoid any organics for the crystallization of some chemicals. That's why in the final work of Medina, we put membrane bioreactors because we want to eliminate any contaminants of organic origin. Otherwise, with normal nanofiltration cannot be done. But the cost of the MBR will easily pay back the investment when you crystallize these kind of things. But anyway, these advantages of this crystallizer, from the one we mentioned before, this is we are able to realize very high specific area for mass transfer. Putting a lot of fibers in your module, you have very high surface available for each one of the pore we are discussing. You can have an optimal control of the supersaturation level, as we have been discussing. As a consequence, we will have a shorter induction period, high value of crystal growth at low supersaturation, and just the possibility to act as a heterogeneous nucleation if you change the chemistry of the polymeric material that you have, the surface energy of the system. These are just some evidence of the sodium chloride. That's the one that you saw also before that we are producing with membrane. This is normal sodium chloride that you produce with normal crystallizer. This is a forced circulation crystallizer. This is a rotating flow. This is a baffle crystallizer. You can see here, we choose the most interesting for us, but you can see how big is the difference between the single cubic crystal that you expect to form and the one that you normally are forming using alternative system. That's the one you saw already. Sorry, let's go to some other story. Oh, that is the interesting, as you can see here, this is an interesting slide because look here, if you change the axial flow rate, the retentate flow rate, this is 100 liters per hour, this is 200 liters per hour, so you are just changing the speed on which your molecules are running on the membrane surface, you can see what is happening. This is at low speed, this is the form of your sodium chloride, if I will remember. This is when you are increasing. As you can see, you have elongation, which is what you expect. You're just inducing, is much easier, the molecule that interact with each other. If you're growing the axial flow rate, that is the one that is coming out compared to what was coming out here. And now you can extrapolate this kind of phenomena. I will mention that you must be careful, for example, on the solubility. The solubility is a function of temperature. So depending in which range you are working, you can induce or reduce the probability to precipitate together different compounds. You can have different form of sodium nitrate, sodium sulfate, sodium chloride. Each one has a typical behavior in terms of the solubility as function of the temperature. And that can be parameter you can use positive, that means if you know and you understand, you can separate in different form, or negative, if you don't realize this and you precipitate something that you don't want to precipitate, and during precipitation you can have a different problem. Remember we talked about the problem of temperature polarization in membrane distillation, very present here and more. One of your PhD students today in ITM is working only on temperature polarization profile in membrane crystallizers, because you have a lot of these temperature polarization profile that you are forming and related to the thermal properties of the material, that means your polymer, and to the heat transfer across the pore of your membranes, depending from how big they are, etc. You can have a different level, different form of temperature profile, which can affect not only the efficiency, but can affect also the final performance of the system. You can not only change the energy consumption, but you can change the form that will precipitate if this kind of data are true. In some cases, they are also more severe than this. And that is some other example how the effect of the temperature can have on the transmembrane flux. This is just a function of time. You can have different form depending from axial flow rate and the different temperature. What I was trying to show you is a little bit different. Are here. I was mentioning until now everything is going okay. But look here, as soon as you start to add something to your solution, which is not exactly which is real, but is not present in the lab state, for example, you put some humic acid. Humic acid is very good representative of most parts of the organics which are present in any in seawater, in river water, brackish water, etc. You can have some interesting effect in negative this time on the performance of your membrane crystallizer. You can have, for example, the relationship between the different geometry of the system is going down significantly. That is increasing the humic acid concentration, you deviate for the initial performance. The transmembrane flux, if I am right here, that was transmembrane flux, as function of time, is going down, increasing the amount of humic acid. So this is one of the effect. What we are adding here is very, very low concentration of humic acid. So any organics present in the system has to be removed as much as possible. That's why I was mentioning we are starting to work with membrane bioreactors to avoid this kind of effect on the habits and on the transmembrane flux of the system. So you can just reduce, you have a lower water recovery factor, you have smaller crystals, higher these variance of the system, lower crystal grow rate, etc., etc. Basically, you have to introduce a new way to pre-treat your traditional nanofiltration and reverse osmosis if at the end you want to obtain crystals from your system. The other effect I was mentioning is the fact that also if you do very well, you separate calcium, for example, but it's very difficult to separate, for example, this strontium, which is present in very low amount normally. I think is few percent, so you don't take too much care. When you buy on your, or you go in your lab and you have, for example, magnesium sulfate, high quality, check carefully the composition
of what you have been buying, you will realize they give you already few percent of strontium is always present, because very difficult to separate, and so you are used to work it. But in our case, it's becoming a problem, because there is a different behavior in terms of the transmembrane flux when you have strontium present or we don't have strontium. And it's not huge, but it is present. More than this, you have some effect on the quality of your crystals. We are talking about making crystallization in a very well-controlled environment with very nice final products. However, if you have some strontium present, the number of crystals with a certain geometry, with a certain length and with a ratio is changing significantly. So the quality you have to check this is not a big trouble, because you know what is happening, but you cannot have exactly the same kind of crystal that we were showing before when you don't have. So this is one, and now we have been studying this effect, but it can be much more than this, by the way. And so you have to learn, if you want to realize industrial level, you have to learn this kind of thing. That's the one that people are looking. That's what is happening today when you are talking about reverse osmosis. Normally, the salt deposits are very nearby, and this is all the brine. Now, this one that can be the origin now are becoming, I think I showed you already some of this number, but just to summarize again, we are just closing. If you remember, I gave you that today we are producing about 65 millions of cubic meter of fresh water per day. Nice, a lot of water. In some country, people are telling today, if you go on the web, there was an announcement from Australia that they are doing this. Israel has no more water problem. They have 5 plants in operation today. They have no water problem. Does not exist anymore in Israel. It was a big problem years ago. Australia is going to tell the same as Israel. We will do the same as Israel. A lot of water, but on the back, there is a lot of, 37 tons, millions tons of salts. What to do with this? So this, if you are using the available amount we have today, the 65,000 with the 37 millions, and you check what is in the seawater, we are talking about magnesium sulfate. Magnesium, you can basically double if you just extract, using membrane crystallizers, high quality epsomite from the magnesium sulfate available, you can double the production worldwide today. Tomorrow can be more than this, and something similar, I think we discussed already, 30% can be lithium chloride, et cetera, et cetera. This is not only case, because that is desalination. A lot of industrial process have the problem what to do with sodium sulfate. Today, when you produce, for example, silica, silica is produced using sulfuric acid to extract the silica from the raw material, etc. There's a lot of sodium sulfate that one time that we're just putting underground again, or today is going to be forbidden by law. So big company, for a French company, for give an example, are working and testing in a different part of Europe, and also not in Europe, what to do with the huge amount of sodium sulfate they are producing together with silica. Silica is very important because silica means many other high added value at the end. One way of doing is to just recover the silica, the sodium sulfate. Also here in a very interesting form. There is one paper that we already published some time ago on the same membrane distillation units and membrane crystallizers. If you understand exactly how to separate the different polymorphs of sodium sulfate and magnesium sulfate, that's a typical study you have to do, and you want to produce this one. You want to produce as in epsomite, as magnesium sulfate. You have to operate in the situation in which you produce epsomite, the added value. Now with sodium sulfate, you can try to produce only thenardite. How to do this? Very difficult, to the point that it was not done with the traditional system. With membrane system, exactly what we are doing today. Today we are producing thenardite. Same story, and just to the recovery of lithium. Lithium is an interesting study. Somebody can just spend some time to analyze, because lithium is a big problem. Lithium consumption will grow significantly, lithium battery and all these kind of things. Lithium is produced today basically in Bolivia, and quite complicate also the extraction, etc. If we want to double and triplicate lithium production, big trouble. Today you can extract from the sea. The same 30, already I showed you before, is 30% increase annual production. There's a lot of calculation already done, not from the membrane people, from the economists, what to do. But you have to reduce the amount of seawater from your big number, from 1,000 cubic meter to few cubic meter. And that is not so easy, but or you have to invent a new form of crystallization. For example, you can create some system non-solvent. You can just introduce in an aqueous solution some solvent that will facilitate the supersaturated formation for the lithium chloride. You can make some complex, etc. So a lot of interesting study, but this is something that has to be carefully analyzed, and you can just try to reduce it. We will stop here, but this story is not yet closed, because everything that we have been discussing now was membrane distillation and membrane crystallizers, basically with the big idea, forget about protein, to extract water from a very high recovery factor, together with eventually raw material from brackish water, seawater, river water, etc. Because the water problem is a problem. But there is another source of water that is very well present and people never think about, which is this one. Any factory, any place where you are having any production line, you have a lot of water that's going in the cooling tower, in the process. And at the end, it's going in the sky in form of this flue gases at a different level, with different level of contamination and so on. If you make an analysis of what is going here, and you see that is all wastewater evaporated, and there are 100 for each single unit. There is 100 cubic meter per hour, and if you add all the other one, are millions of cubic meter per hour that are produced in different countries. Now, if you find a way to avoid this and produce water, this is basically water, and a few percent of. And that can be quite interesting. There are different ways of doing today. Is liquid absorption, cryogenic, cooling condensation, the same. And finally, there's another one, which is just membranes. And membranes can operate in two different ways. One can be just using membrane selective for water, and so water can go, gases can go across, and water cannot go, or vice versa, depending if it's hydrophilic or hydrophobic. But traditional gas separation system, the humidification. But what we are interested in another way of doing. This was a big project in Europe, dense membranes or membrane condenser. This is the way of doing that we call a membrane condenser. And membrane condenser is a system in which what you can have is that your saturated gas stream arriving from the pipe from the different industrial production can go across your membrane system. And that will be, again, hydrophobic microporous membrane. Don't tell around, exactly the same that we have been using for making membrane distillation and membrane crystallization, with one difference. In membrane distillation and membrane crystallization, you had a liquid phase arriving on your membranes, and we were warming up to evaporate and moving the vapor across. In this case, you're using the same membrane, hydrophobic microporous, but instead of warming up, you are cooling down. This gas is normally arriving at a temperature of 90-95 degrees centigrade. High temperature, the one coming out from the chimney here. If here you put this temperature on the membrane surface, not 95, but at 80 degree, you cool down 8 degree, 10 degree, what is happening here, you can condense at least 20%, that was the goal of our project, but more than this, you can, depending what you want to do, you can have 50%, 90%, depending from the delta T between temperature of the flue gas coming out and the temperature on the membrane surface. So if you realize a system where you don't warm up, but you cool down, membrane distillation is becoming the same module, in principle, is becoming a membrane condenser. And also here, as we learn that you can have more than just crystals or evaporation, you can have specific crystals, etc., you can see that when you are starting to work on this, you can have a new kind of condenser in which you can control, for example, the level of contaminants. Because what is coming out from here is not just water. It's water plus, depending which kind of production you have here, fluoridic acid or ammonia or sodium sulfate, depending from the kind of pulp, textile, pulp and paper industry, etc. And how to keep control of the quality of the eventually using the traditional technology, not easy and complicated to the point people normally are not doing. With membrane system, you will learn that again, controlling, understanding the mechanism and controlling the system, you can condense water with no fluoridic acid or water full of fluoridic acid in such a way that you know what to do to reuse, to use another part, etc. So also this one is a quite interesting system in which exactly the same kind of configuration, except that the water in this case is formed on the membrane surface and nothing is going through in water form. Also here gas are going across. Oxygen, nitrogen, eventually contaminant vapor phase. That is again a typical example of what we call the flexibility of the system. In principle, when these things will arrive on the market, these things have been just, you will read papers in the last now or in the next few months, not too much in the literature until now, but this kind of system will be presented as new membranes, new model, new configuration. Forget, we understand exactly the same that you are using for membrane distillation. If you know how to handle and you change your boundary condition, etc., you can operate the same module, the same membrane in a different, total different application. And that is very important. We meet next week. Thank you.